Okay, welcome to this video. Today we're gonna learn how to actually implement the Dijkstra's algorithm in Python. So I recommend you guys watch a video of Dijkstra's algorithm that I made previously, and also there is another video, a link to another video that I put in the description, that's showing y'all our way of thinking to tackle this problem. So one very important thing about Dijkstra's algorithm in this video is that we're going to be using a priority queue. So priority queue in this video is gonna be used as a sort of a method uh, that's going to rearrange elements in a list in an ascending manner. So from the lowest number to the highest number. You don't need to understand priority queue in depth, but all you need is just, we're gonna be using that as a method. You know that Dijkstra's algorithm, we always need to determine the node that has the lowest distance from the current node that we are working on. So let's dive right into it. So first of all, we are going to import the method heap queue, priority queue. And then in order to create the tree we need to work on, we're going to create a class, an object called tree. This will basically make our job easier to create a tree. We're gonna initialize self, and we're gonna make sure that it's a dictionary. So okay, and then self. Okay, so this is going to initialize the tree, and then we're going to create a method called attach. Attach is going to, what attach is going to do is going to link two nodes and assign a distance in between them. So self, so letter one is going to be the first node, and letter 2 is going to be the second node, and weight is going to be the distance in between those two nodes. So there's gonna be two situations possible. First of all, if the node 1 is already in the tree, and the second situation is when node 1 is not in the tree. So first situation, we have this letter 1 in self.tree.keys. Then we're going to proceed as follows. Self.tree letter 1 is going to be equal to letter 2 weight. So what this is going to do is going to add the nodes to which letter 1 is connected, as well as the weight. And then of course we want to document as well the second node, all the connections that are related to the second node. So we're going to do if letter 2 in self.tree.keys a call self.tree. This is basically going to lead to the same result. Letter 2 letter 1 weight. Okay, else self.tree letter 2 Okay, so the first part of it, this part over here, is going to update the tree if letter 2 is not in the tree yet, but this is going to create a new entry in the dictionary. And then the second situation, else self dot tree letter 1, this is going to update the tree, so we're gonna write update letter 2, wait, and then same principle as before. If letter 2 in self tree b is equal to self dot tree letter 2 b letter 1. Okay, 1, wait. So this is basically the same as okay, self dot tree letter 1 is equal to wait, but we want to make it more readable, so we're gonna do b is equal to self dot tree letter 2 b letter 1 is equal to wait. And second case is self dot tree letter 2 is equal to letter 1 wait. Okay, that's what we have. And then we want to create a method that will allow us to display the tree. For that, we're gonna do def display self earn self dot tree. And then to make the tree easy to manipulate, we're going to make sure that it gets turned into a dictionary. So for that, we're gonna do def dictionarize. Okay, I don't care. Self return self dot tree. So it's already a dictionary. But in order for us to utilize or use that tree, we're gonna have to dictionarize it. Okay. So now we're gonna dive into the actual algorithm that's going to solve the problem. So we're gonna call the method def solve tree. So tree is going to be the tree object that we just created, so that we will create. Start. We're gonna want to ask the user. What's gonna be the initial node where the algorithm is going to start from, and then of course we want to convert that to a string. So we're gonna be string input. Ask the question initial node. So what's the initial node? Ask that to the user, and it's gonna be saved into the variable start. And then end is going to be the final node where we want the algorithm to actually end. And I'm gonna ask final node. So those two variables are going to be the two nodes in which between which we want to determine the shortest distance. And then of course we're going to start our current node according to the Dijkstra's algorithm. and the distance between this current node and the first node is actually 0. So we have current node is equal to 0 and start. Okay, so this is going to be in a form of a tuple, right? So we have the value of the node over here, and then second index, index 1, we have the value of the node. So this is a distance from the first node to the actual node that we're working on. This over here is the value of the node, the name of the node, if you will. And then the initial current distance is going to be 0. So current distance. Alright. And then we're going to want to dictionarize to turn the tree into a dictionary. So for that we're going to use the method that we created here, and we're gonna write s3 is equal to tree.dictionarize. Okay, so the word dictionarize may not exist, but I just created a method for that. So dictionarize, make sure I did that correctly. Yes. Make sure that's correct. And then what we want to do is actually initialize our priority queue. Initialize priority queue. Visited set, and the index of visited node. So if you work on an algorithm, you're going to see the usefulness of all of these 3 variables. And then we're going to create a loop which is going to iterate over all the nodes that are connected to the current node that we are actually working on. So we're gonna name a variable b, and then, well, b, this is the beginning of the loop. B not equal to true. So we want the loop to end when b is equal to true. But yeah, as I said, we're gonna iterate over all the nodes that are connected to the current node. So for I in S3, current node 1. So current node 1, this, as I said, is going to be the letter, the name of the node, because that's the second index that over here. That's over here. Okay. S3 node. So current distance is going to be S3 current node 1 I is current distance I. So what this is going to do is going to find the current distance. So you have actually a current distance which is 0, and this is going to be updated by adding the distance from the node to our current distance, and I is simply going to be the name of the node. And then we're going to avoid that node if it's already been visited. So we're gonna write if current node 1 index visited. I'm gonna pass. We don't want to do nothing if we've already visited that node, or else what we want to do is to add the current node to the priority queue if we haven't visited it yet. So cd, and we're going to add that to the list of the visited node, visited set. And we're gonna add the corresponding index to index visited, of course. And what we're gonna do next is actually rearrange the we're gonna rearrange the priority queue so that the lowest value comes first. And for that, as I said, we're gonna use the method heap queue dot heapify. Heapify is the method that comes with heap queue. It's going to rearrange priority queue. And then what we're gonna do next is to create a while loop. We're gonna create a while loop, and the goal is to extract the node with the smallest distance from the initial node, from the priority queue. For that, we're gonna say while a is equal to false. Current node is equal to heap queue dot heap pop pq. So with the method heap pop, we're going to be able to extract the smallest value from pq. Pq is the priority queue. So priority queue is going to be updated automatically, and current node is going to have the value of the tuple that has the lowest weight. If current node 1 in index visited, as I said, we don't want to work we don't want to work from we don't want to work with values that have already been visited, so we're gonna keep a false in this case. That's probably not necessary, but I'm just writing it down. And then else a is equal to true. So if it's not in the index visited yet, we can stop the loop. A equals true. And then we will have reached, and then we're gonna make sure that we didn't reach the end of the tree yet. So if we actually reach the end of the tree, if current node 1 is equal to end over here is the final node. If we reach the final tree, we want to make b true. So if b is true, then this loop is going to end. Else we're gonna update current distance. Else current distance, okay. Current distance is going to be current node 0. Current node 0 is the value of the distance of our current node from the initial node. Okay, so that's what it is for the value of the shortest path in between start and end. Start and end are the two nodes. What we want to do is to actually print the distance. So return current node 0. That's gonna return the distance. But if you wanna actually look for the path, the shortest path between those two nodes, we're gonna have to follow some extra steps. So we're gonna go backwards. So we have the distance from the shortest distance from the initial node, right? And we reached the final node. But what we're gonna do is that we're going to work backwards. So the code for this, I'm going to write the code for this. Node 1. The current node, current distance, current node. That's the current node distance, and then we're gonna set those variables that's turned out they turned out to be very useful later. Or equal to false. All right. While QQ is not equal to true. So we're gonna look at the tree, and then we're gonna look for all the weights that are attached to the current node. So for key value in CL items, and then we're gonna subtract the current value of the node with different weights and see if it matches the value in visited nodes. So don't worry about understanding it because it's kind of difficult without paper, but I'm just writing the code. If you just want to get the distance, then you can just stop over here. Return node 0. So over here, this is going to output the shortest distance between start and end. But the second part over here is actually going to I'm gonna work on restoring the path, retracing the path that we follow to get the shortest distance. So I'm gonna remove return here. Key value items. For j in visited set, if it's gonna match a value in the visited set, just to confirm that the value is the same. I'm gonna print this one. So this is going to print the node that we're passing through, and then update the current node 1, current distance 0. Break. So we found a value, so we're going to break out of the for loop, and if this first for loop here, but if break for is equal to true, then break out of everything. But if we didn't, for example, if we didn't break out of it, so we didn't find any value, we're gonna return we didn't break anything if that is not true. this value of if here is not true, then we're gonna come back to this until break for is equals to true, and we're gonna break out of everything except from the while loop, and then if the current node that we're working on is equal to the first node, then it's equal to true. Okay, breakout. Okay, it's supposed to be here. Else QQ false. That's it. It's gonna print. This is going to print the path and return here, and return this is going to return the distance. That's it, we're done with this. That's it guys, we're done with the code. What I'm going to do is to build a tree that is based on the first tree that I presented on the previous video about that Dijkstra's algorithm. So declare an object tree, and then we're gonna attach A, B, 6, A, C, D, 8, D dot attach D, E, 10, T dot attach D, F, 15, T dot attach G, E, 2, D dot attach G, F, 6. Alright, according to the previous video, the distance is supposed to be 19, so I'm gonna check. T is the name of the tree, so solve T, initial node A, final node G. Okay, there you go, we have 19, and working backwards, we have first G, E, D, C, A, that's the path, shortest path. So final answer is like A, C, D, E, G. That's the final path, shortest path between A and G. And the shortest distance is 19. Alright guys, that's it for this video. Thank you for watching.